Okay, Bob Swanson here, ICC astronomy instructor, and we are at the last lab activity of the semester. This is Module 12. The topic is habitable zones. Not easy to say. Essentially, where can life be found, not only around our star, the sun, but perhaps around other stars. Of course, this is somewhat biased because we only know of one form of life, and that is a carbon-based life that needs water to survive. That's us. And so again, you're going to be at the Module 12 lab activity. You click on the student guide. Again, we're going to work through this student guide. Click on the simulation. That's going to take you to this page. Not as many background pages as we saw in the last module, but please do read through the life in the universe. Again, this talks about what are the chances? Well, shucks, we're only one planet around one star, but there are 100 billion stars in the Milky Way galaxy, and 100 billion galaxies in the known universe. So statistically, it would appear that, as we've also studied, there's most stars have at least one planet around them. So statistically, there's good chances that there might be other life out there. Is it carbon-based? Does it need water? Those are other questions that are interesting. But as far as just the statistical chances, it might be pretty good. So you can read through the life in the universe section. What's most important, and what we'll be studying in this activity, is what's called the circumstellar habitable zone. It's essentially what's called the Goldilocks zone. Notice that for a sun-like star like ours, which is of moderate temperature, that green area is the Goldilocks zone. It's neither too hot, we're not too close, the Earth is not too close to the sun, so we're not too hot, in which you couldn't have liquid water. We're not too cold. We're not too far away, and therefore too cold to have liquid water either. So we can have liquid water at the surface. That's really, really important in order to have life. So that's what that whole section talks about. We'll get to this galactic habitable zones a little bit later. But first of all, the circumstellar habitable zone simulator. What this allows you to do is to see a particular star. You can choose the star mass. So in this case, this is the sun. It's got a mass of 1, and notice my planet is 1 AU away from the sun. So it's Earth. And notice this was the distance, and it also gives the luminosity of the sun, all that kind of stuff. The temperature. So this is essentially our sun. And what you can do is, on page 2 of the student guide, you're supposed to change your star mass and determine what the circumstellar habitable zone looks like. So in the case of the sun, this is row 3 of the table. Its luminosity is 0.739. The inner boundary of the circumstellar habitable zone, this blue area, what you can do is just drag your Earth until it's too close and it gets too warm. Notice how it turns from being Earth to a desert. Well, so that's going to give you essentially the position. About 0.819 is the boundary of the inner boundary of the CHZ. And then out here, where it becomes too cold, becomes kind of an ice ball, that's the outer boundary of your CHZ. And that's going to be around 0.89. And that's all you have to do for the first table. Okay. Moving on to one thing also you should mention, I should show you. I'm going to reset this and bring it back to the way it originally was. There's a little timeline down here, which is kind of fun to actually hit run, and you can actually make it run kind of slow. I'm going to slow it down a little bit to show that as the star evolves, as it changes, notice you can watch the star on its HR diagram, and over time the star will change. It'll spend most of its lifetime on the main sequence. This is about when the sun is about 5 billion years old, which is its current age. And notice that eventually the habitable zone, as the sun heats up, it's going to shift the habitable zone a little bit farther out. And so Earth may not be habitable in its current position for it's a long as far as the human lifetime is, but eventually Mars might be a little bit more suitable in its position away from the sun. And eventually, as time really goes on, notice how the sun will eventually work its way off of the main sequence. And we're going to see what's called a helium flash, in which it's going to shed some of its mass. And it'll do it actually a couple of times, and then eventually become a white dwarf, in which case, notice now the Earth is really going to be out of luck. It's going to be way, way too far away from this tiny little white dwarf that will eventually cool down into a little cinder out in space. Again, nothing to worry about in the near future. On page 3 of the simulation, they want you to open up different systems, 51 peg, and they want you to zoom out. Now, the way you zoom out is you shift and click, and then just kind of drag and hold until you get to the point, and they'll ask you a question about the habitable zone around this particular star and what that planet, this planet that orbits 51 peg, what its chances are of having life on it. And you can pretty well tell that it's pretty far away from the habitable zone of that particular star. It's not likely to have life. And that's the way this whole that's the way this whole simulator works. Now finally, on the near the end of this activity, page 7, they talk about the galactic habitable zone. So now instead of just looking within a solar system, now we look at a galaxy, which is, of course, each star potentially has a solar system around it. So it's all these stars around the center of the galaxy. And it turns out that certain solar systems are more likely to have life than others. They're not all equally likely to have life. It depends upon the location of the solar system, or that star, within the galaxy. It turns out, and as you move this little ring, or if you move either the ring, actually I guess you have to move these little lines here. As you move the line, it'll move the ring. And notice that for our sun is kind of in a sweet spot for 2 reasons. First of all, it's close enough to the center of the galaxy that there's a lot of building material. You need to have, in order to have terrestrial planets, you need to have metals and silicates, heavy elements. And the abundance of heavy elements increases as you get closer to the center of your galaxy. So you would think, well gosh, well then a lot of life should be found near the center of the galaxy. The problem with the center of the galaxy is there's a lot of stars there. And if there's a lot of stars there, that means you're going to have a lot of supernovas. And supernovas emitting gamma radiation are most likely going to kill off any life that is getting afoot into evolution. So that's the downside of being close to the center of the galaxy, is because it's so crowded, you're more likely to have exploding stars, in which case early life could get snuffed out because of those explosions. So therefore, the sun is actually in a pretty good spot. It's got enough building material, but it's far enough away from the center that supernova explosions are not common occurrences. Alright, that's all we got. Hope you enjoyed the class.